Hello, I'm Darren Korn, and this is my submission for EEE 120, Lab 1, half adders, full adders, and 4-bit adders. So now, the first adder we were tasked to make was a half adder, which essentially adds two bits, A and B, together to have the output of a sum and a carry, a 1 and a 0. And to test this works, we add 1, which just equals 1. Or we add a 0 and b is 1, which is again just a 1. And then in a case where we're adding 1 plus 1, we should get a carry of 1, which is 1, 0 in binary, which is a 2 in decimal. So 1 plus 1 equals 2. Now, to prove this in a GTK wave, I have these values, which at 0, all outputs are 0. At when either A or B is 1, the output of sum is 1, as you can see here. And whenever A and B are 1, we get a carry of 1 and a sum of 0, which is demonstrated here. Now, the second circuit we were tasked with designing was the incrementer. So here that is now, using 4 half adders, an A input, a 4-bit A input, an incrementer input, we can demonstrate a counter with a carry. So to show this, when the incrementer is off and we just implement any hex value of A, and we increment that. So currently A is 1, Y is 1. And if we increment that, we get A is 2, Y is 2, and so on and so forth until we all the way to any hex value, the hex value of F, which is 15. And then once that is 0, it just restarts. Now, what makes this different than just a counter is that we have this incrementer button. So say we have D, and then we turn on this incrementer. All of a sudden, that D on the Y value becomes an E. So this incrementer essentially adds a 1 to your input. And where that can have some differences in outputs is when you are at, say, the F value, because at the F value, that is the highest value the hex can go in the ones place. And so when you add 1, you get you move on to the second place, which would be worth 6 with a weight of 16, as opposed to a weight of 1. So when I have F in the Y column, but when I add the incrementer, I get a 0, because now we have a 0 in the ones place and a 1 in the 16th place. So we'd get a 1, 0 in a hex, which is 16. And that is the incrementer. To prove this, we have the GTK wave for the incrementer, which is here. So here we go. Whenever the incrementer is on, as you can see, the value of Y in comparison to A is 1 greater. And when you get to F here on the A value with an increment of 1, we get a carry of 1 and a Y of 0, which is a 1, 0 in hex, like I said, which is a 16 in decimal. And then once the incrementer gets turned off here, the Y values start matching the A values again. So 1A equals 1Y, and so on and so forth. And that is the incrementer in circuit and waveform. Now, the third adder we were designing in this circuit was the full adder, which can be written as this. I also wrote it as 2 half adders combined. It's just a difference in notation, and you're not using 3 input, but I did it as the example shows for this demonstration. Now, to prove that this works, this once again is like the half adder, except it has 3 inputs now, so we can add 3 bits together. So the max number that this thing can output is a 3, right? If we had 1 plus 1 plus 1, that equals 1, 1, which is 3 in binary. But just to prove that it works, you get 1, 1, 1. So no matter which input, as long as only one's lit up, we get a 1. And then if 2's lit up, no matter which inputs, as long as there's 2 lit up, we get a 1, 0, like the half adder. This is all the same as we were doing before. Except this time, if we have 3 inputs, we can get a 1 and a 1. So now the sum and the carry out can be lit up at the same time. So we can get a 3, a 1, 1 in binary. Once again, to prove this, we have the GTK wave of the full adder here. And once again, so at 0 to 10 nanoseconds, we have nothing because there's no inputs. And then from 10 to 20, anytime that we have 1 lit up, so 10 to 20, 20 to 30, and 40 to 60 nanometers, as you can see, as long we have 1 input on, and so our sum equals 1. The moment we have 2 inputs on, our carry is 1 and our sum is 0. And that's at 30 to 40, and that is also at 50 to 60 nanoseconds, and 60 to 70. And then the only other condition that we have is when all 3 are lit, are in the on state, and we get a full ones of 1 plus 1 plus 1 equals 1, 1 in binary, which is 3 in decimal. And that is the full adder and its functionality. So the fourth and final circuit we were tasked with designing was the 4-bit adder, the 4-bit incremental adder. And here it is. It does work. Now, I can't exactly prove this with just the simulation, and so I'll take you to the GK wave in just a second. But essentially what it does is it adds 2 4-bit hex values, 4-bit in binary, and then they turn out to be hex values when we translate them, using 4 full adders, and it accounts for the C in and the C out, as well as the sum and the positive or negative overflow that we have, due to the fact that when adding and having, I guess, overflows or carries, it can make the sum positive or negative based on 2's complement because we only have 4 bits to work with. So yeah, so this is the simulated adder, and it does work. But to prove that, because it's easier, I'll take you to the GTK wave. So let me do that now. Here is that 4-bit adder testing specific curated combinations, as there are like 512 of them. So I tested a few kind of general tests to show that specific elements of this circuit work. And so it can be used as a kind of general guidebook that, given any other element, it would also work for those. So the first test that I conducted was just the 0, 0, 0. It's basically the false test. Everything comes out as false because everything is false. A 0 plus 0 equals 0 with no overflow and no C out. The next test I want to do is just basic addition. 1 plus 1 equals 2. No C in, no C out, or no overflow. So this is just a basic adder. We were able to do that with the half adder, but this can also do it as an adder. The next test I did was with testing hex addition. So using 2 numbers, I got a hex number. Now technically the 4 and the 8 are hex numbers, but I'm saying like using 2 binary numbers, say you did it in binary, it gave you a value of a hex, or a value of, see, it basically gave you above 10. So that's what I wanted to show, that you can get letters out of it. This is 12, so 4 plus 8 equals 12 in decimal. The next test I wanted to do was testing the carry out. So here we have a hex 15 and a decimal 15 and a decimal 1. 15 plus 1 is 16. However, in hex notation, you can't have 16. So it results in a carry out. So in hex, f plus 1 is 1, 0, which in decimal is 16. So that just shows hex addition here. Or sorry, carry out. using hex numbers. The next test I conducted was testing the overflow with signed addition. So when adding, these are two positive numbers. Once again, like I said, because we have 4 bits, we can only show a 3-bit number. So the max number we can positively show is 7, because once we get into that 8, which is 1000 in binary, that's all that last significant bit is used actually as the sign calculator. It shows the sign of the number. So this is a positive 7 and a positive 3 added together, which gets you 1010 in decimal, or an A in hex, which is actually a negative number because, like I said, we have that most significant bit, the leftmost bit is a 1, so it's a negative 10, which means that we have an overflow. So here we have an overflow of 1 because it is negative, and 10 because that is 7 plus 3. The next test that I conducted was overflow with sign subtraction. So just like I did with the last one, it's kind of the same vein. It is, except I'm using negative numbers. So because 9 is greater than 8, it's going to be a negative 9 because 9 is written as 1001. So we have that 1 in the leftmost significant bit. Same goes with B, which is 11. So we have negative 9 plus negative 11, which should give you a negative 20. And sure enough, that is exactly what we get. But it's kind of harder. You have to do some more math to see that. And the way that we see that is because in hex, negative 9 plus negative B gives us uh, a negative 1, 4, or I guess just a 1 and a 4 with an overflow of 1, which essentially is negative 20 because, like I said, when we have a C out in hex, that is equivalent to 16. So 16 plus 4 is 20. With that overflow of 1, that shows that it's negative. Next, we have testing the carry in value. So, or actually, I got them out of order. Here, one second. I'll I'll just continue with this one. This one actually tests all three, the carry in, the carry out, and the overflow all working in conjunction. So we have the 9, the B, which, like I did earlier previously, that gives us the negative 20. However, here we are also implementing the cin function, which just adds a carry in to the whatever we're adding together, which will give us in total negative 21. And here we can see exactly that. So we have the cin plus the previous numbers, and all that happens is that we, instead of getting a 4 as our output, we get a 5, which is in hex, that is 1, 5, which is 21 with that overflow of 1, so it's going to be negative 21. And then our next tests for the overflow due to a carry in. So here what I have is a 4 plus a 3. Now those both are positive numbers. They're signed, they're positive. However, I'm also adding a 1. So I'm adding a 4 plus a 3 plus a 1. Now, even though these are both positive numbers, because I'm adding that cin, we actually get an overflow because we get an 8, which, once again, that's 1000, which has an overflow because we're only allowed to use those first 3 bits. So we get an 8 with an overflow, which is a negative 8. So once again, just showing that we can use the carry in as a way to get us an overflow. And then lastly, we have a test for the carry in to make sure that it works properly. So we have a 3 plus a 3, and this is like the previous problem or the previous test where you add the 3 plus 3 plus 1, but this time you get a positive 7 because 7, we can represent 7 without an overflow because it in 4 bits is represented as 0, 1, 1, 1. And so using the carry in, we can just add a third number. And that was the conclusion of all my tests. Those are all the tests I felt that we needed to prove that this would work in a general sense as a 4-bit incremental adder. Thank you very much.